Hi everybody, I hope you're doing okay. We are starting actually a new section today with our first lesson on distance learning. Before break you guys had a test. I'm going to be getting those test results to you guys pretty soon. But I wanted you guys to kind of think back on what we were learning before with exponents. You will need a calculator for today's lesson too, so if you need to use your phone or if you have an online calculator that works for you, that would be awesome. All right, guys, we take a look at your warm-up question. It says to select the equivalent expression. Before break, we learned that if you have an exponent on the outside of a set of parentheses, you distribute it to both of the exponents or both of the factors on the inside. When you do this, you're really multiplying your exponents. So x would have a power of -3 times -7, so that would give you positive 21. And same thing with your y value. You'd be having 3 times -7, so that would give you y to the -21. We learned before that you had to simplify further with negative exponents, but for now, we can look at our multiple choice answer and see that that is correct. Also, a blast from your past. Which relation is a function? Remember the vending machines with my peanut M&Ms? If you had a domain, so your input values, if I pushed B5, it looks like we have a problem here, right? I'd be shaking the machine and getting peanut M&Ms and a Twix bar. So this would not be a function because it's good for me, bad for the machine. If I look at the second choice, B2, peanut M&Ms. B6 gives me a Hershey bar. B9 gives me Reese's Cups, or peanut M&Ms, but that's okay because it's so popular that it's created two different spots. And then maybe this then down here would give me Reese's Cups, okay? So remember, if every input leads to its own output, that would be perfectly okay. Again, there's a problem in this one here at the domain value of 0. We can see that we're getting two different peanut M&Ms at the same value, or getting a peanut M&M and a Hershey's bar on one input. So this would be the correct answer. Again, if you read carefully in the assignments on Google Classroom, it's up to you if you want to print out the note taker or not and fill it in as you go. You're not going to be turning this in or anything. If you'd rather just take notes on a separate sheet of paper, that would be perfectly fine as well. But today we're going to be reading and writing numbers in scientific notation. So we're going to be really dealing with numbers that are really, really, really big or numbers that are really, 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 really small. So your essential question is, how can you read and write numbers in scientific notation? So, scientific notation is a number that is written in scientific notation that is represented as the product of a factor and a power of 10. The factor must be at least 1 and be less than 10. So if you've ever actually just punched a whole bunch of zeros into a calculator and just kept on hitting it because maybe you were bored and you figured out, okay, finally I'm going to hit the enter button and see what happens. Sometimes it'll give you these really, really like weird things, or you'll see the letter E pop up on the calculator, because what happens is your calculator cannot support that large of a number or that small of a number. So how it does this is it kind of represents these large or small numbers with scientific notation. So there's two parts to it, and it has to pass this test. Your first part has to be a number between 1 and 10. So if I cover up behind the decimal point, do you see how you have an 8? 8 is between 1 and 10, so it passes the test. And the second part is it has to be a power on 10. You can have a positive power or a negative power. Since this has a negative power, this is actually a very small number that we have here. Very, very tiny. All right. If we take a look at these examples, we're going to tell whether they are written in scientific notation. So the first part I'm going to do is I'm going to look at the number in the front. Cover up anything behind the decimal point. I have a 2. Since this number is between 1 and 10, it's good for the factor. If I take a look at the back part of it, I have times 10 to the -9. Since I have a power on 10, it is correct and it is in scientific notation. So tell whether the number is in scientific notation. Yes, it is. And we're going to say factor is between 1, and 10. If I look at question number 2, look at the first part. If I cover up the 5, 0 is not a number that's between 1 and 10, so it doesn't pass the test. So this is not a number that's in scientific notation because your factor is less than 0. Actually, I'm sorry, less than 1. Okay, so standard form is what we typically think of when we see the really, really, really big numbers or the really, really small numbers. So writing a number from scientific notation to standard form, the absolute value of the exponent tells you how many places to move your decimal point. So if your exponent is negative, that means you're going to be moving your decimal point to the left to see what the actual number is. If your exponent is positive, you're going to be moving the decimal point to the right, and you're going to see how large of a number that you're dealing with. You can also use your calculator to double check, but sometimes the calculators can't hold that big of a capacity. So for our first one, we're going to first write that number in standard form. So the first thing you're going to do is you're just going to recopy the factor. Okay, now I don't see a decimal in this problem, so what we're going to do is we're going to put a decimal in. So I'm going to use my smiley face to represent a decimal. Okay, now the next thing that I'm going to do is I'm going to look and see what the exponent is. Exponent of 7 means that I'm going to be moving this decimal point, or my smiley face, 7 places. And if I take a look at the previous step, I know that if I have a positive exponent, I'm going to be moving this decimal to the right because I have a really, really big number. So when I start doing this and start moving this to the right, I'm going to fill in with how many zeros. So 1, 2, 3, 4, 5, 6, 7. And I double check that with my decimal point. I can start filling in with the zeros. There we go. Here's my decimal point. 1, 2, 3, 4, 5, 6, 7. And I'm going to fill that in with zeros. So every little bump stands for a 0. All right, so to write your final answer, you're going to write a 6 with 1, 2, 3, 4, 5, 6, 7 zeros. So 1, 2, 3, 4, 5, 6, 7 zeros. And remember, you're going to put a comma for the big ones, right? So this would be 60 million after every 3. Okay, let's do the same thing for the next one. We've got 9.9, so I'm going to start with 9.9. This one has the decimal point to start with, but this time I can see my power on 10 as a negative. So what that means is I'm going to be moving it not to the right this time, but to the left because I'm going to be dealing with a really tiny decimal. So I'm going to move it 5 places. 1, 2, 3, 4, 5 places. And I'm going to do it with my smiley face so you guys can see it. Okay, here's my decimal point. 1, 2, 3, 4, 5. I'm going to put that as a little placeholder. And I'm going to fill in with any bump with a 0. So 1, 2, 3, 4. So when I write my final answer without the smiley face and the little bumps, I'm going to have a decimal point in the front, 2, 3, 4 zeros, and 2 9s. Okay, so that's your answer for question number 2. Same process for 3 and 4. So if I have 1.285 times 10 to the 4th, I'm dealing with a large number because I have a positive exponent, so I'm going to be moving my decimal point 4 places to the right. 1, 2, 3, 4. Okay, so if I move it with the smiley face, here I go to double check it. 1, 2, 3, 4 to hold that place. I'm going to put the 0 in for that missing bump. And then finally, I'm going to write my final answer without the decimal point at the end because I'm dealing with a large number. If you left it, it's okay, but you definitely want to make sure for these smaller numbers that you're putting it in the front. But your final answer is going to be 12,850. Let's do one more. For question number 4, it's 2.75 times 10 to the negative 3rd. The negative exponent tells me that I'm going to be moving my decimal point to the left because I have a tiny decimal. So I'm going to be moving it 3 places. So 1, 2, 3. And again, move in the smiley face. 1, 2, 3. And I'm going to fill in my zeros with the extra bumps. And then finally, I'm going to write my final answer. This time I have to put that decimal point there, right? So 0.00275. Make sure you don't write 2 decimal points. Make sure you just have 1 decimal point in your final answer. All right, so this is one of my ultimately favorite questions because it sounds so silly, but it actually involves a little bit of scientific notation. It says an object with lesser density than water will float. An object with a greater density than water will sink. Use each given density in kilograms per cubic meter to explain what happens when you place a brick and an apple in water. Sounds silly enough, but what you're going to do right now is actually change all 3 of these numbers to standard form. And you're going to see, if you put a brick in water, is it going to sink or float? Okay? So let's do that right now. I'm going to pause the video and have you guys try out how to change each one of those to standard form. So hopefully you've got a chance to pause the video and try out this problem. But in the problem, it tells me that I have a lesser density than water, it's going to float. So when I actually used my scientific notation and moved it 3 places to the right, I found that the water's density is 1,000, and I think that's what in kilograms per cubic meter. Did the same thing for the brick, moved it 3 places, 1,840. And then same thing for the apple, but this time I only moved it 2 places because the power on 10 was a 2. So because the brick has a greater density than the water, that means that this is going to sink. And then, since the apple has a number that is smaller than 1,000, this one will float. I know, shocking. You're very surprised that this is happening. But just to give you a practical application with scientific notation, one thing that you might notice though is look at the power on 10. Since you have a higher power on 10 of the brick than the apple, this number is ultimately going to be bigger than the apple's number. And that's actually a shortcut that you can use for this next problem. So when I'm trying to figure out which star has the highest surface temperature, the first thing I'm going to do is I'm going to look and see which one has my highest powers on 10. So it's either going to be Bellatrix, the Sun, or Rigel, because these are the ones that have the 10 to the 4th powers. The next thing I'm going to do to make this go quicker is I'm going to look at the factors. Since they all end in the tens place, there's nothing really that I need to worry about. So which one is the largest number out of the 3? Well, the factor that has the 3.8 is the biggest factor out of each one of those that have 10 to the 4th power. So the correct answer for A is Bellatrix. For part B, which star has the lowest surface temperature? Well, I'm going to take a look now at the powers that are smaller. So I'm going to look at, I guess you'd say that is Betelgeuse, maybe? I don't know. And then Aldebaran, because these ones have powers of 10 to the 3rd. So the next thing I'm going to do is I'm going to look and see, okay, which one has the smaller factor? I'm comparing 6.2 with 7.2. So this Betelgeuse, oh no, I've said it 2 times. If you have seen the movie, you know exactly what I'm talking about. Betelgeuse, good movie to watch while you're on break. That is the correct answer for this one. So what I want you guys to do is just pause, try the next activity, and then there will be another lesson on how you do the flip-flop version of this as well.